question. Has the age of the universe also increased in line with the increased redshift? So you're saying that we've multiplied over the course of the last 30 years, redshift has gone from 5 to 6 to 14 or something?
No, the age of the universe of the standard model is derived from the theory directly, not from the observations. You have some free parameters, of course, depends on the free parameters. And the free parameters have been more or less the same in the last 25 years. The last big change in the free parameters was in the end of the 90s with the proposal of the dark energy. The dark energy has introduced a big change. And this, indeed, there was a problem. Before the dark energy, there was some tension because the universe was too young compared with the oldest objects observed with the globular clusters or others. But after the introduction of the dark energy, the omega lambda, the age was more or less, has become more or less stable, 13.7, 13.8, with now the accuracy with which we can determine is better because we can measure the parameters with more accuracy, but it's more or less the same. There were not such a change. However, as you said, the redshift of the galaxy that we can observe now is much higher than in the past. This is so now we can observe the universe when it was much younger than in the past. Redshift 5 or Redshift 6. Redshift 6 is one giga year. If you go to Redshift 14, as I said, it's like maybe 300 or 400 mega years, more or less. So now we can go to the universe when it was 3 times younger than previously. And these are what is generating the problems because there are surprises. In the past, we have built a theory based in our knowledge for the universe at redshift lower than 5 and 6, and we have extrapolated and everything works perfectly. In the moment in which we go to observe galaxies at much higher redshift, we find that things are not working so well. And possibly if in the future somebody builds a new telescope, a new satellite, even better than the James Webb, difficult to imagine because it's so good, the James Webb, it will take a very long time to build something similar or much better than this. But maybe in 20, 30, 40 years, we will have something better. Possibly we will have, again, new surprises, for sure.
Okay, so if they're not getting the age from the redshift, which seems to have changed over the last 30 years, can you tell me how they get the age from the model?
Simply from the cosmological parameters. Once there are many parameters in this, but the most basic ones from the standard cosmological model are 6 parameters, and these parameters are measured with the data, with the supernova, with gravitational lensing, with the cosmic microwave background radiation. The more information you have, the more precise you can determine these parameters. Now we have more precision than in the past. This is why we can determine with more precision. The error bars are smaller, but however, it's not so different. I mean, for instance, mainly the main parameter that determines, also other parameters take place, the omega m, omega lambda, but perhaps the most important one is the H naught, the Hubble constant. Nowadays, well, we are discussing, there are several groups, whether it is 67 or 74, there are some tensions, but this is the same value that was more or less measured 20 or 30 years ago. The only difference is now that the error bars are much smaller. In the past, we measured 70, maybe plus minus 5.
And they're different values, right? Depending on whether you look at the CMB versus
the... This is called the Hubble tension nowadays. There are 2 main groups in cosmology, one related to the cosmic microwave background radiation, and other related mainly to the supernova and Cepheids, and also you need to calibrate the supernova with Cepheids and other elements, but these are related with the observations of galaxies. And nowadays, they claim they have a tension. I mean, the value given by the cosmic microwave background radiation is around 67 plus minus 0.7, something like that. However, for the supernova, they claim it's 73 or 74 plus minus 1. So there is a 5 or 6 sigma tension. However, I have to add that, in my opinion, these error bars has to be better estimated. There may be some systematic errors. So, in other words, possibly some researchers are being very optimistic in the claim that they can determine the Hubble constant with 1% error. It's not clear. People who claim that these errors are correct and the measurements are perfect, they say that there is a problem either with the standard model or something that we don't understand in the physics, why the Hubble constant measures in different systems is different. However, there are possibilities, and it's not impossible, that these differences come from not taking into account some systematic errors in the way of measuring the things. For instance, maybe I explain you. In the cosmic microwave radiation, apart from measuring the radiation coming from the cosmology, from the decoupling matter radiation, there are many foreground contaminations coming from our own galaxy, coming from other galaxies too. So the technicians, the experts in this CMB, they need to subtract the contaminants. They claim they can do it perfectly. They claim, okay, we know perfectly how is the galaxy, the zeros of the infrared zeros of the galaxy. We extrapolate the emission in infrared, we subtract in microwave. They claim it's perfect. However, and it is well known, once you do the correlation of the clean CMB maps with the galactic maps, either from our galaxy or other sources, still you find that there is some correlation. This means that your map is not totally clean. There are some residuals. And if there are some residuals, possibly the error bars with which you measure the cosmological parameters are larger than what you claim. So you are being too optimistic claiming that your map is totally clean of foregrounds. With the supernova, there are many other problems, because in order to know the distance, the relation of the distance and the luminosity of the supernova, you need to calibrate with Cepheids, and there are many intermediate stages for making the calibrations. And also, there is something which is quite evident, and people know it. People know that it's a small problem, but they sometimes ignore, is that they are assuming that the supernova are all the same in the local universe and in the distant universe. They claim they are standard candles. This means this star has the same luminosity here and at the beginning of the universe. It's the same. This is not totally correct, I will say. This is an assumption. And if you make...
Well, they've been wildly wrong about that in the past, right? I believe that the first estimate with the Cepheids confused two different types, and they actually ended up having to change the age of the galaxy by like 2x. I forget who it was. I could look that up.
If one can follow the history of the measurements of the Hubble constant, indeed I have been doing some analysis of this, you can see that there were always some tensions. There were always, throughout the history, some different groups measuring different values. So it's not only a question that now in the 2020 or 2019 we have found a discrepancy between two groups. No, there were always some different groups, because there are different ways to measure, to calibrate the things. It's quite normal. During the 20th century, in the last 2 decades, in the 70s, 80s, 90s, there were two big groups using extragalactic astronomy. There were two groups, and one of them was measuring a value of 50, around 50, was the group of Sandage and Taman, very important astronomers. Sandage was a disciple of Hubble, for instance, was a very good tradition of a North American astronomer. And then there was the group of de Vaucouleurs, a French astronomer with a big group, and they measure a value of 90 or 100. And during 20 years, they were complaining to each other that the others were not doing correctly the measurements, because they were totally convinced that their values were correct. in the end, it was solved in some intermediate position. It's not 50, it's not 90, it's 70, it's something in the middle. And this was I would say, the consensus position. No? Now the people in extragalactic astronomy agree that it should be around 70. So the problem is now that we have different ways of measuring the cosmology with the CMB and with the supernova, and still we are finding that there are some discrepancies of 10%. But in my opinion, I will not give so much importance to this discrepancy, as it can be due to many systematic errors. I will even interpret these values within 10% as a success of the prediction, that rather that they are very similar. 67 and 74 are quite similar to each other. But of course, it's one of the hot topics nowadays in cosmology. How to solve the Hubble tension is one of them.
So I did look this up. It was Walter Beatty? Walter Beatty? Yeah. I guess they had confused originally classical and type 2 Cepheids. And this was leading to almost, I think, half the age of the galaxy that they had originally. Or actually, they doubled the age of the galaxy as a result of this. My point is that there's ample precedent for confusing these standard candles, as you will. And the more that we learn about them, it could certainly reframe how we think about these systems in a dramatic way sometimes.
Yes, but as usual, all this information, what you have mentioned about Bade, what I have now told you about the discussion between Sandage and Taman and de Vaucouleurs, and this should teach us that the measurements in astronomy have many sources of errors. So we should not use one single measurement of few single measurements to support any revolution in science.